Okay, so next up, we're going to take a look at phase diagrams. I actually love phase diagrams. They're pretty interesting because they're very intuitive. So a phase diagram is exactly what you think it is. It's just the different diagrams of when we expect phases to essentially exist. So we have two axes that we're interested in. So along the Y, we're going to have pressure. And typically we're going to have pressure in atmospheres. Again, it can be different depending on this type of substance you have, and we're going to see a couple of those. And we have temperature, and we're going to put it in degrees C along the x-axis. Okay, so we have pressure and we have temperature. The typical phase diagram is going to have a series of lines. So there's going to be a couple of curved lines here. There's one straight line with an arrow. It kind of extends, continues on. I probably could extend that a little bit more. And then there's this terminus right here. And they all look slightly different, but that's ultimately what we have for the phase diagram. We'll get into what all this stuff means, but that's what we have. So each of these regions is a different phase. You don't have to memorize which phase is where if you can just kind of think to yourself, all right, well, where would these phases actually be? So if I look at something that has a very high pressure and a very low temperature, what phase, solid, liquid, or gas, do we expect? So up here, again, low temperature, high pressure, we would expect something to be in the solid phase. So this is in fact the region for a solid, okay? Same concept, a very high temperature and a very low pressure. And pressure is holding things together, right? That's why solid, high pressure, we expect to see solid. Low temperature, because there's not a whole lot of energy, we expect to see solid. Now, if we look at the reverse of that, really high temperature, things are moving really rapidly, really low pressure. So this region right here, low pressure, meaning there's not a whole lot holding these things together. That's right, you'd expect this to be a gas. And in between that, we're going to have liquid. So gas, liquid, and solid based on the differences in pressure and temperature. So that's what we have. Every time, so how these things work is essentially, let's say, all right, let's say we start at certain temperature and pressure, and then we increase the pressure. Well, what phase do we end up in? What kind of transitions do we go through? What phase are we in now? So you kind of see those transitions when you're looking at these problems. So across this barrier, if your substance or if your, I guess, problem crosses that barrier, you're going from a solid to liquid. That's going to be melting or fusion, more appropriately fusion, right? Right. Going from solid to liquid. If you're going from liquid to solid, right, that's going to be freezing. That freezing. And then I'm just going to move this up a little bit. I guess I could have left it there, but there we go. So that would be fusion, melting, and freezing. There we go. If we're going from liquid to gas, if we're transitioning from liquid to gas, that is going to be vaporization. If we're going from gas to liquid, that is condensation. And then finally, going from gas to solid and solid to gas. So solid to gas is going to be sublimation and deposition for going from gas to solid. Okay, so there's our phase diagram in all of its glory. I guess let me add some things to the axes. It's probably not appropriate that we just leave it as is. So let's see here. So this little point here, which we're going to look at in a second, is at 5.2 atmospheres. This point up here is at 73 atmospheres. All right. Okay, that was moments for you, but it was a little bit for me. So back to what we were talking about. so we have our phase diagram. I was filling in the the axes. So by the way, I guess there's like a little break there. So the jump from 5.2 to 73 is pretty massive. So let's put that there. At this point, these points are important, the two that I'm kind of marking here. So those are somewhat important. And so we have negative 57 degrees Celsius there, and this one would be 31 degrees Celsius. Okay, so we're all set. So let's label a handful more things. So this point right here, that point right there is known as the triple point. The triple point is where you have three phases that exist at the same time. Yeah, so all three phases exist at the same time. In fact, I'm going to pause it again and I'm going to play it, and I'll link this below in supplemental material most likely. So let me just find it. All right, I can't seem to find it, but I will link it. Cyclohexane triple point. That's, you should look up on YouTube or on Google and you'll see the clip of it. But it's pretty crazy. You're going to see, you're going to essentially see all three phases exist at the same time, which is a really weird thing, but we'll see it in a second. So this point right here is known as the critical point. So we talked about critical point in the last chapter. Critical point, again, is where it can no longer exist as a liquid. So we have this little area over here. So this region in this upper left-hand corner, so this whole region up here is known as it's known as a supercritical fluid. It's kind of not so much a gas, not so much a it's not so much a gas, not so much a liquid. It's kind of in between. Again, you should Google, and I'll post something for a supercritical fluid as well. It's kind of a neat little thing, so worth taking a look at. Okay, so this is our phase diagram. A couple of things. So this triple point exists at 57 degrees and 5.2 atmospheres. So if you're given, so this example down here, what phase changes are anticipated if CO2 at 1 atmosphere and negative 90 degrees Celsius, so I don't know, we're about here, is heated to 0 degrees Celsius followed by a pressure increase. So we're going to increase the pressure or temperature to about here, and then we are going to increase the pressure to about 70 atmospheres. So what has happened? Well, we have gone from, actually, let's make it a little bit simpler, or a little bit more complex rather. So let's say that this happens to be 1 atmosphere, and then over to about 70 degrees or 0 degrees Celsius, and then up to 70 atmospheres. So going from negative 90 at 1 atmosphere all the way up to 70 atmospheres, or sorry, 0 degrees Celsius and 70 atmospheres, we've gone through 2 phase transitions. We've gone through sublimation followed by condensation. So that's the kind of question that's going to ask, what transitions do you expect to see? What phase are you in? What phase are you in at, I don't know, 10 atmospheres and 20 degrees Celsius. So 10 atmospheres, 20 degrees Celsius, maybe around here, you have to be a gas. What about 30 atmospheres and negative 40 degrees Celsius, right? So here, so that's the kind of idea for what a phase diagram will tell you. All right, good. And so with that, let's just take a quick reminder and what this looks like, and then let's take a look at water. Do you notice anything different between this one and water? I'm sorry, this one and our example. By the way, this is in fact CO2. This is a phase diagram of CO2. So this one versus this one. What you'll notice is this is actually slanted in the other direction. Okay, so because it's slanted in the other direction, that's just something that water does, because water acts weird. So that's what we've got. What we'll also notice, and this is more prevalent for something that we use pretty frequently, this is my normal pressure, right? So this is the standard pressure that would be 760. So we have 1 atmosphere. And a 1 atmosphere makes this the normal freezing point and the normal boiling point. Again, normal freezing point and normal boiling point. Actually, that's the normal freezing point, normal boiling point. These are occurring because they just happen to appear. This is where those things, and those are the temperatures at which they sit under the pressure of 760 torr. Okay, so that's the phase diagram of water. Pretty straightforward. These are really neat little diagrams. You can pull a lot of information out from them. In fact, could we reach the triple point of water? Temperature would not be a problem at negative 0.01 degrees Celsius. We can do that right now. But the pressure of 4.58, that's pretty low. So that would be a little bit difficult to get to. So we need the vacuum line and some high vacuum. Interestingly enough, everything has a phase diagram. So this is the phase diagram of carbon. What you notice is this is the phase diagram. If you wanted to make synthetic diamond, you can absolutely do it. So if we look at our temperature of, so right here is just normal day-to-day carbon. 1 atmosphere, actually, sorry, that's where the unit comes in, a gigapascal. A gigapascal is a giant unit, right? So we have to recognize that we're pretty far off there. So graphite is the most stable version. So we're like down here. So this is the most stable state. But if you wanted, the main way to make diamond is to actually chemical vapor deposition. So you increase the temperature to convert it to vapor. Then you increase the pressure to create diamond. So that is in fact how they create diamond. They start with vapor and then they convert it through, so they take graphite, heat it up, take that vapor, turn it into diamond. Again, avoiding going through the solid state phase because that gets a little wonky. So you want to start with something where you don't have any bonds at all, which would be a vapor. So yeah, everything has a phase diagram. You can usually figure out what is the most stable version of something based on, and again, I should also mention that diamond is solid. These are all solids. This is a solid. So there can be multiple regions of solids or liquids or gases and those types of things, but really just solids because they have different forms and we can actually study it. But yeah, that is it. That is the phase diagrams. Carbon, there we go. And we'll move on to solids next.